Okay, so let's start. So I think you all know that. We have an exam on Wednesday here. Please don't bring a lot of stuff with you because it's going to be dense. So try to put everything on the side. Bring just pencils, and that's it. We'll give you everything else. Closed book. I know that many of you have been working on it, so there are examples on the website. We are going to cover everything that we touched in class and in the homework, no more, no less. And please go to the recitation. So today there are going to be 2 hours. It's on Piazza and on the website. Please go and ask questions. That's the main message. I also want to tell you something that hopefully you also know. We released homework 1, the graded homework 1. I think the numbers are very nice. So I split it here to graduates and undergrads because there are always questions on should we grade it separate, curve it separately or not. It's very similar. We'll see how this goes in the rest of the semester. But anyhow, it looks like you all did a pretty good job on that. Questions? If you have questions, yeah.
Will the session today be recorded? Or?
It will not be recorded. We cannot record it. But we did it 2 hours, so 3 to 4, 4 to 5, so hopefully it will fit everyone's schedule. So we cannot record it there. Yeah. It's 2 separate sessions, yeah. So we'll see how it goes based on the number of questions and the dynamics, but that's the plan, yeah. Other questions? Yeah. For quiz 6, yeah, I think we should be able to put it up, yeah. I'll check. Other questions? If you have questions related to the exam, please do it now rather than at the end because everyone is interested. Yeah. So the issue is that who cannot make the first hour and can make the second hour? A few. So you should take this into account when based on how you plan. Okay. Yeah.
That's kind of a specific question, but on one of the exams it talked about the difference between the stochastic gradient descent perceptron and batch perceptron. I wasn't really sure if perceptron's only worked one example.
So in the exam we probably define what we mean. It's true. Perceptron only works one at a time, one example at a time. So maybe it was talking about batch gradient descent. I don't know what you're talking about, but we can either look at it or you can ask again in the recitation or in my office hour. Okay, so let me move on. This is where we are. So we talked about theory of generalization, and we actually brought up 2 questions. The original theory assumed that we have a consistent learner. That is, someone gives you M examples, and you manage to learn to produce a learner that is completely consistent with these M examples. And then we said, okay, if you manage to do this, this is how well you're going to generalize. And the how well was a function of the M examples, the number M, the size of the hypothesis space, and of course the epsilon delta, how much you wanted to generalize. Now, so this brought up 2 questions. One is, what if we don't manage to be consistent with the M examples we see? Two, what happens if the hypothesis space is not finite, because everything we did was a finite hypothesis. So at the end of last time, we addressed the first of these questions, and we gave this result. So we said an agnostic learner, it's called agnostic because it doesn't care about what the target function is, and in general, it will not be able to be consistent with the target function. So an agnostic learner which makes no commitment to whether f is in H and return the hypothesis with least training error over at least M examples, this M, can guarantee with probability at least 1 minus delta that its training error is not off, but by more than epsilon from the true error. So if you take these many examples, the difference between what you observe, your empirical error, your training error, and what will happen in the future is bounded by epsilon. And you can see that this M is really a function of the size of H again. So to summarize everything we've done in this area, both for the case of consistent learner and non-consistent, the more realistic case, non-consistent learner, if you take these many examples, and this many example has to be polynomial in this ln size of H, you're going to be okay. Question?
So the difference between this formula for M and the previous one is that in the previous one, you assume that your algorithm was consistent with the M examples in the training set. And then what is the relation between this type of, I guess, bound and the specific ones we learned for perceptron, the novice one?
Oh, okay. Excellent question. So what is the difference between this bound and the stuff we've done for perceptron, the Novikov theorem? Anyone wants to risk an answer? Yeah.
In perceptron, we talk about the number of mistakes. They're talking about the total number of examples.
Right. So Novikov theorem, perceptron says, I don't care what you see. It could be a very adversarial sequence. But I tell you that the data that you see is linearly separable. And we also gave this complexity parameter gamma, so how separable it is. Under these conditions, you will make these many mistakes, and that's it. In the future, whenever you see data that is also separable with this gamma, no more mistakes. So that's just mistakes. I don't know when you're going to make these mistakes. You know, maybe you'll see 100,000 examples, make on them 7 mistakes, and only after the 100,000 you'll start making mistakes. I don't know when. Here, it's number of examples. So take examples, find a learner. You can do it with perceptron, you can do it with decision trees, you can do it with whatever you want. With neural networks, find a learner that made its best effort on this data. I don't know how many mistakes it made. I don't know what is the training error, but some training error happened. The true error is going to be some gap between the training error and this gap is going to be epsilon, the same epsilon that is written there. So if you want very tiny epsilon, small gap between what you've seen in the training and what you'll see in the future, you'll have to look at a lot of examples. If you care about 20% gap, you don't need to look at so many examples. But this is in terms of number of examples. How will you generalize in the future?
So then you're saying that different algorithms, if the hypothesis space that you choose is the same size, the bound will be the same.
Yes, excellent. So if I use linear separators, doesn't matter which linear separator algorithms I'm learning, same generalization. This is an excellent observation. Basically, it means, so in the machine learning literature, there's thousands of papers written because they did not understand this. People compared between different linear learning algorithms in the limit. Now you know from homework 2 that there is a difference between linear learning algorithms. Some of them, in the case of sparse data, learn faster, some of them learn slower, but in the limit, they're all going to generalize the same because everything really depends on size of H. So you take SVM, you take perceptron, you take Adagrad, you take your favorite linear function. If they've seen enough examples, they're going to do the same. All of them will converge to the same thing. Not necessarily the same function, but its generalization properties are going to be the same. This is what this theorem says. Yeah.
Clarify what you mean by true error.
True error is the true error over the distribution. Right, so there is some notion of true error when you sample example according to the unknown distribution. Right? So we are assuming all the time here that there is some distribution that governs the generation of the examples. There is, let's assume, a true hypothesis. So there is a notion of a true error. Basically, we defined it as the probability that your h of x makes the right prediction, or the expected value that your h is making the right prediction over expectation taken over d. I don't know how to compute it, of course, but this notion exists. What we know how to compute is the expectation over the training data, which is what I call training error, or in the previous slides, error subscript TR. So the true error is what you are expected to see in real life once you already have a model and people are giving you examples. Yeah.
In the case that you have consistency, then you don't have any training error, which is the training
Consistency means training error equals 0. Yeah. So this generalizes what we've seen before, only that this bound, if you really look at it, is a little bit worse because there's epsilon square. In the consistent case, there was epsilon. But, you know, these are minor details. Really, it's a generalization of the consistent case. The consistent case is a lot more intuitive, and we could basically prove the theorem on one slide. This case is a little bit harder. So we haven't proved it, we just claimed it. Okay, so that addresses one of the questions that I asked. What happens in the realistic case where I'm not consistent, but rather over my M examples, my training data, I'm going to make some mistakes. The second question is the finite case. So far, everything is quantified by this log size of h, which is unrealistic because in real life, in many cases, we are going to use infinite hypotheses. What can we say then? And this is the example that I ended with last time. I want to learn a concept that is an axis parallel rectangle. Let's say 2 dimensions. So I care about can you play in the NBA, and I'm going to look at height and weight of people. So it's kind of plausible to assume that if you are between this height, and between this weight and this weight, you can, otherwise you cannot. Simplifying things. So basically that's what is going to happen, right? So I'm going to see some examples, positive and negative. I told you that the true concept is an axis parallel rectangle, but it's real valued axis. So the numbers are real valued. The number of possible rectangles is infinite. How would you learn if I just give you positive and negative examples? What would be your learning algorithm? Yeah?
Maybe just bound the pluses. Like you can say on, like, well, you have to do a rectangle, you can take the max of the x and y coordinates, and the min, and that will create a rectangle that can encapsulate the pluses.
So take the positive examples, find the max and mean x and max and mean y, build a rectangle, and say that's my rectangle. And that's going to work, right? Because I told you the data is consistent with a rectangle. So you'll start with this. I give you more example. You extend it. And overall, that's what you're going to do. So you feel that you can learn this rectangle, but you don't know how well it's going to generalize. And the theory that we gave last time isn't sufficient because I have too many rectangles. So what I want to do today is I want to augment this theory to the infinite hypothesis space. And again, just like before when we said small hypothesis spaces, small h, and large hypothesis spaces, large a, we have the feeling that even when you're infinite, there are some small infinite hypothesis spaces and large infinite hypothesis spaces. So they differ in expressivity. Yes?
Why is it that the hypothesis space is infinite? You should say that it's consistent with rectangle. So what?
How many rectangles are? X is parallel rectangle in 2 dimensions.
A lot of them, but you have a set of data that you have to do rectangles. Like, I understand what you're saying, but like, there are many rectangles we can draw, but still, like, we have a limited amount of m's that we are putting the rectangles based on.
So you write that given a fixed amount of data, there's a finite one that separates the data. But you don't know what data I'm going to give you tomorrow. So in principle, the class is infinite, right? Just like linear separators. You can also say, for a given amount of data, fixed amount of data, there's probably a finite amount that I can consider. But when I see more data, maybe the finite number that you considered isn't doing it, right? You should have considered more in order to separate it when you union also the new data. So we really have to consider an infinite amount. But actually, as I'm going to show, we can think about it as finite in some sense. But that's basically what I'm trying to do today.
Because you, like earlier in classes, you would give us like you give us the examples, give us the output, and then you ask us what is that possible space. In this, you're saying that we don't know what n is. Like we don't know what example we'd be given, in what sense we given. So it's an infinite hypothesis.
No. The hypothesis space is infinite because it's infinite. Because every rectangle is defined by 4 numbers, say, 4 real-valued numbers. The set is infinite, right? So it has nothing to do with the data. It's true that, given a finite data set, I could prune the set of rectangles and to say, I really care about these options. But that's just because you were short-sighted. You just looked at a small number of examples. In general, you may need more in order to really do the learning with respect to this.
But in that sense, do you not say everything will be infinite? Because if a rectangle has 4 points, you have to define it's infinite, then any hypothesis space will be infinite. You wouldn't know.
Not the space of conjunctions. Okay? So, but it's true, there's a lot of hypothesis spaces that are infinite, but again, there are sizes of infinite. And the size that is important here, you can think about rectangles, and you can think about convex polygons that have up to 17 sizes. There's more of those than of rectangles. Or you can think about convex polygons in general. There's a lot more of that. You can think about linear threshold functions, and you can think about conjunctions of linear threshold functions. 2 linear threshold functions where the hypothesis is this and that. Think about how, in the plane, this is going to look like this x here, where one of them says positive above it, the other one says positive above it. So if you do and, it's positive also in this intersection, right? So this is a more expressive class of functions. So both are infinite, but one is more expressive than the other. So we want to be able to deal with expressivity of hypothesis spaces that are infinite. So we need a measure for this, and the measure is something that is called the Vapnik-Chervonenkis dimension, VC dimensions, and it's going to be analogous to the size of H. When H is infinite, we're going to replace basically size of H by, or log size of H, by VC dimension. So what is this? So the key concept that we want to address is something that is called shattering. So here are points. These are data points. I think there are 13 data points here. And there are many ways to label these data points, right? I can take, okay. So I can take the most extreme right points to be positive and the rest negative. I can take two of them, the most extreme positive and the rest negative. Can you hear me up there? Okay. And so on. So for each one of the 2 to the 13 ways to color these positive and negative, some functions are going to separate it, but some functions or some classes of functions may not be expressive enough to separate it. So that's the notion of shattering. Let's start simple though. Let's start with 2 points. If I have 2 points, I can define the function this way. The top one is positive, the bottom one is negative. I can separate it with a linear function. I can define it the other way around. The bottom one is positive, the top one is negative. I have 2 more options, right? I can say that both of them are positives. I can say that both of them are negative. So when I have 2 points, I have 4 possible functions. But linear functions are enough to separate it. Any combination of positive, negative of the 2 points, you can use a linear function to separate. Everyone agrees? Now, when I have these 13 points, if I color it this way as positive and negative, you can see hopefully the red, dark red, and orange. I can separate it with a linear function. But if I color it this way, it's a better mix of orange and red, I hope, then a linear function will not do it. There's no linear function that will separate it between red and orange, right? If I really want to separate it, I need a very complex function. So that's the idea here, right? So the idea is that linear functions are not expressive enough to shatter. By shatter, I mean here, separate all possible labelings of these points. And this brings me to a definition. So I'm going to say that a set S of example is shattered by a set of function H if every partition of the examples in S into positive and negative examples can be realized by a function in H. This function in H is going to give exactly these labels to the examples. So for example, let's go back here. So this blue function, or the blue class of functions, that you can be expressive as much as you want, can shatter everything. Any split of orange and red points that you'll do, you'll find this blue curve that does it. But linear functions are not enough, because for some splits they can do it, but for some splits they cannot do it. So let's start with with simpler classes of function. So here's the first class of function I want to consider. These are functions that are expressed as left-bounded intervals on the real axis. So the function is 0 to a, parameterized by the number a. So everything that is between 0 and a is a positive example. Everything that is above a is a negative example, right? So that's a class of functions, right? It maps a point from the real axis into positive or negative. Now, if I give you 1 point here, you can shatter it. One point can take 2 labels, positive or negative. Let's say I give you the point 7. How would you shatter it? Is there a class of functions in this that can make this both positive and negative? Which function will make the point 7 positive? What was it? A is going to be 9. If you choose A9, then the point 7 is positive. Which function will make my point 7 negative? A equal 2 will make it negative. So a given point can be shattered by this class of functions. What about 2 points? I'm going to give you 2 points now. 0.7 and the 0.9. Can you shatter it with this class of functions? Yes, no? So 2 points can be labeled in how many ways? 4 different ways. Let's assume that both of them are positive, okay? 7 and 9 are positive. Give me a function in the class that does it. A equal 10. If I want both of them to be negative, 7 and 9 are negative, which function in this class is going to make them negative? A equals 6. Now I want to make the first one positive, the 7 is positive, and the 9 is negative. Which function will make it? A equal 8. Now I want to make 7 negative and 9 positive. Which function is going to make it? No function. So there's no function in this class that can label all 4 possibilities. Everyone agrees with that? So sets of 2 points cannot be shattered. What I mean here is that given 2 points, you can label them 4 ways. At least one of these 4 ways cannot be realized with a function in this class. Okay? And that means that the set of 2 points cannot be shattered. Okay, here is a more expressive class of functions, intervals defined by 2 parameters, a and b. So now, again, you have to think about it as a set of functions, right? It's a set of functions that they take a point on the real axis and they map them to plus or minus, right? And the set of functions is parameterized by these a and b. Now, if I give you 1 point, clearly you can shatter it. If I give you 2 points, you can shatter it. Think about the example that I had before. The 7 equal negative and the 9 equal positive. With this expressivity, you can deal with it, right? What if I give you 3 points? What would you do? 3 points will have how many different labelings? 8 different labelings. Give me one that is not realized by this. Yeah?
If you want 2 like outside ones to be plus in the middle.
Right, so I'm going to choose, let's say my points are 5, 7, and 9. I'm going to label the 7 as a negative example, the 5 and 9 as positive examples. No function in this class can realize this labeling. Everyone agrees? That means that sets of 3 points cannot be shattered with this class of functions. Okay, let's move up. Another class of functions, half spaces in the plane. So these are linear functions. I'm in 2 dimensions. And I want to figure out what's going to happen here. So again, you can think about 1 point, 2 points, 3 points. It will be easy for you to see that, say, if you have 3 points, you can label them any of the 8 ways, and you will find a linear function that does it. Right? If all of them are positive, you'll put the linear separator there. If all of them are negative, you'll put it down here, and so on. You'll be able to do it. What about 4 points? Yes?
So back to 3 points. What if they're collinear?
Okay. What if they are collinear?
You have plus, minus, plus all on the line. How would you separate that?
Okay, good question. So, and that brings an important subtlety here. Not all sets of 3 points can be shattered, but some sets of 3 points can be shattered. So I can give you 3 points in the plane for which I can shatter with linear separators. Okay, so we have 2 quantifiers here. Given a set of 3 points, and now I'm going to put the 3 points in general position, not on the same line, can I shatter it or not? Let's think about it. General position 3 points, can I shatter it with linear separators? Are you convinced? Who says yes? Who says no? Okay, you're all convinced that general position I can shatter. So there are sets of 3 points that I can shatter. Daniel comes and says, well, but there are sets of 3 points that you cannot. If they're on a straight line, you cannot. And that's true. So my condition is going to be, that's why I brought this yellow thing, and my condition eventually is going to depend on there are sets of size 3 that I can shatter. Not necessarily all sets of size 3. But we agree that there are sets of size 3 that I can shatter. What about 4? For 4, I would argue that no sets of 4 points can be shattered. Anyone wants to explain why? Idea? Okay, so we already agree, yes?
So you take 3 of those points, you shatter them, whatever you want. Your 4th point is going to end up on one side or the other. When you switch that label to the opposite of what that classifier says, it's not going to be.
Okay, that's a good direction, but you have to say something more because maybe there's another one. I can do something to my linear separator and then shatter it. Right? I did not say that it's the same one, the same function that shatters all labelings, right? There is something in the class of function that does it. Not necessarily the same one does it for all sets. So I need to be, but that's the right intuition. But let's do it this way. So if they are collinear, we already agree that there's no way we can shatter, right? So let's deal with the general position. So I have 4 points. And let's build the convex hull over these 4 points. Okay? Let's assume that all the 4 points sit on the convex hull. Right? So think about it as a square or rectangle, and the corners are my 4 points. Can you shatter it? Or give me an example of why you cannot shatter it. How would you label it so that it's not shatterable if they are corner of this convex polygon? Do alternating, right? So take plus, minus, no linear separator is going to do it. So that's one option, when the 4 points are sitting in the corner of the convex hull. The other alternative is that they are not. Only 3 of them will be the corners, and 1 is going to be inside. How would you label this case? Yeah?
You can't separate them.
Yes, so basically you'll do a different label. So these are the 2 situations that I consider, and this is enough. Yes?
What if you have, imagine that 2 space, you have positive, negative, what can you choose?
Okay, so this is the picture that I have here, and if I have positive, if it's alternative colors.
In that case, you can, but what if you don't have alternating? You have like 2 positives on one side, off the corner, and 2 on the other.
Yeah, then I can separate. But again, the issue is I have 4 points in general position. What I want to argue is that I cannot shatter it. What does it mean that I cannot shatter? It means that out of the 2 to the 4, 16 possible labelings, there's at least one that I will never be able to realize with linear separators. Many others I can. In these 4 points, if I want all of them to be positive, I can do it. If I want the top 2 to be positive and the bottom 2 to be negative, I can do it. What I cannot do is I cannot do the alternative labeling. Yes?
How is it different from that 3 points collinear?
Okay, good. That's exactly the question that I want you to ask. So notice that we have 2 quantifications. So in one case, I fix the set of points. And what we said to Daniel is, some set of points you will not be able to shatter, but some set of points you will be able to shatter. Let's fix this set of points that I claim that I can shatter. What does it mean to shatter? That for this fixed set of points, all labelings are realizable. In your case, we fix the set of points, and I'm showing you, you cannot realize it, right? There is one labeling of them that I cannot realize, okay?
Fix the location. The location.
I fix the points,
Fix the point.
and for this set of points, I cannot realize. So it's important to keep our quantifiers intact, and I'm going to emphasize it again. So now that we understand kind of what is shattering, and again, I want to emphasize it. Sets of 1 or 2 or 3 points can be shatters. It doesn't mean that all sets of points can be shatters, but there is a set of 1 points, this point, that I can shatter. There's a set of 2 points, this, that I can shatter. There's a set of 3 points. Take just a triangle in the plane, I can shatter. No set of 4 points, I can shatter. So fix me a set of 4 points, choose whatever you want. At least one of the 2 to the 4, 16 labelings is not realizable. Okay, so with this we can define VC dimension. So what is VC dimension? It's going to be a way for us to quantify this notion of expressivity. Notice that we moved 3 steps. We moved from very simple set of functions, just one-sided intervals, to a more expressive set of functions, 2-sided intervals, to a more expressive set of functions, linear separators in the plane. And we show that the size of the set that can be shattered goes up. Indeed, if you have an unbiased hypothesis space, I mean all the functions are there, you can shatter anything, right? Basically, every set of points that you're giving me, there's going to be an element in this set of functions that will shatter it, that will realize a specific labeling. But once we do not have an unbiased hypothesis space, we define the set of functions, then it's not going to be the case. And then we're going to, hopefully we argued already or exemplified that the larger the subset X that can be shattered, the more expressive the class of function, the hypothesis space is. That is less biased. Okay, so here is, again, the definition that we had for shattering. Again, we said that a set S of examples is shattered by a set of functions H if for every partition of the examples in S to positive and negative labels, I can find a member in H that does it. Okay? Now I'm going to say that the VC dimension of H is the size of the largest finite subset of X that is shattered by H. And again, this issue that we talked about, it's the largest, is the size of the largest subset of X. It doesn't mean that all subsets of this size have to be shattered. There has to be a subset of this size that is shattered. Again, let's go to this case of 3 points that we showed. There was a set of size 3 that was shattered. Not all sets of size 3 were shattered. But no set of size 4 was shattered. So this is where the threshold occurs. Some sets of size 3 were shattered, no sets of size 4, and this is going to define the VC dimension to be 3. Right? Because 3 was the largest finite subset of X that was shattered. So let's go back. And so this is the emphasis. Even if only one subset of this size does it, still, it's the largest finite subset of X. So let's use this definition now and think about what are the steps then to show that VC of H is D. Yes?
I'm kind of confused by the 2 different definitions. So we're saying that a set S of examples is shattered if for every partition there's a function that we can label them the way we want to, but then for the VC dimension where like even if one subset is shattered, like I don't understand how there's like one definition where it's like 1 and then another one where it's like all.
Right. So there are 2 quantifiers here. So we are looking at subsets of points. and we care about the size of the subsets. Once you have a subset, let's say it's of size 7, there are 2 to the 7 possible labelings of it. So once you pick a subset, and you look at all 2 to the 7 labeling of it, you want to find in your H class of functions, functions that realize all these 2 to the 7. Right? There's going to be 2 to the 7 different functions because there are different labelings. So that's one quantification. The other one is, I ask you, what is the largest subset that you found that can be shattered? And you can tell me, I found a subset of size 3. That's good. But I did not ask you, is it the case that all subsets of size 3 are shatterable? I don't need that. All I need is to find one set of size 3 that is shatterable. So you see there are 2 quantifications here. So one is, I need one set, one subset of a specific size. How do I know that this subset qualifies? I need to look at all possible labelings of this subset. Okay? We're going to look at least one more example. Yes?
So we used to look at how many H's we can have to be able to separate like the points that we have. Now you're saying that we don't even look at that anymore, we just look at how many points of the points that we have can be separable, or can be shattered by that H that we give. So it's a linear function, we just look at how many points we can. So let's say you're given like 100 points.
So let's finish the definition and go back to this. So what I want to do is I want to argue, I want to explain what does it mean that VC of a hypothesis space is D. There are 2 conditions. One is that there is a subset of size D that can be shattered. If I find a subset of size D that can be shattered, then the VC dimension of H is at least D. And if no subset of size D plus 1, I cannot enlarge the subset. No subset of size D plus 1 is shattered, then the VC dimension is less than D plus 1. So these 2 together are going to say, well, so VC of H is exactly D. Now, what are the points that I'm playing with? This has nothing to do with training data, right? This is just, I have an instance space, X, right? My function in H are defined over this instance space. You just imagine points in this instance space and you make this argument on them. So it has nothing to do with training. The argument eventually is going to be that if you know the VC dimension of H, it's going to say something about how many training examples you will need from this space. Let's take another example, right? So in the case of half intervals, 0 to A, we showed really that the VC dimension is 1 because we took 1 point. It doesn't matter that we took many 1 points, right? It was sufficient to work with the point X equals 7. We showed that it's shatterable, right? We took 2 points. No 2 points could be shattered because when you have 2 points, one of the 4 configuration was left point is negative, right point is positive, and that's not shatterable. Yes?
So that's true because we said that like everything in the interval has to be positive.
Yes.
But if we said we could flip the signs, then that would hold.
I'm not sure I get it.
Like
What
if
is
we
it?
said we could define the interval, that the half interval, to be the negative examples or the positive examples.
Okay, so that's a new class of functions. So define your class of functions.
A half interval that can be of either side.
So basically you say my class of function is defined by A, where the interval 0A is negative, A infinity is positive.
Or the other way around.
No, no. Okay, so you want either, or you want this new class of functions?
The new one would be the same VC class, but the either one would be bigger.
Okay, so we already define now three classes of functions. One class of functions is functions that are positive in 0 to a and negative a infinity. Class hypothesis space number 2, positive a infinity, negative 0 a. And the third class of function, positive either in 0a and then negative a infinity, or positive in a infinity. Okay, so let's think about this class of functions and see what the VC dimension of it is. 2 points.
Yeah, I think it would be 2, right?
What about 3 points? Let's take 3 points.
It's no for 3 points, right? If you say it has to be 0.
Everyone, let's convince oneself. So what we have to argue is that no set of 3 points is shatterable by this, right? So let's take 3 points. Let's take them 3, 5, and 7. How many configurations are there? How many labelings are there? 8, right? Give me a labeling that no class in this function can shatter. Yes? Positive, negative, positive. Now, if the class is on the 0a plus, it will not do it, right? If the function that you choose is from the a infinity plus, it will also not do it, right? Because it has negative to the positive to the left of negative. So for this labeling of positive, negative, positive, no function in your new hypothesis space can do it. Therefore, you define a new hypothesis space with VC dimension equal to 2. Okay, so hopefully this game was helpful. Thank you. So we just define on the fly a new set of functions. It's more expressive than the 0a that I proved, and it's different than my second row here, the intervals. It's a different class of functions, right? Everyone agrees? But it so happened that it also has VC dimension 2, and we just proved it. Okay? So that hopefully this also clarifies the notion of a class of functions. You can define a class of functions many, many ways. You're the owner of the class of functions. And then you can look at it using these tools and say, how expressive is my class of functions? Questions? Yeah.
VC ratio will always be less than or equal to 3
VC of what?
of H.
Why?
Because you can only shatter it if it's less than or equal to 3 points.
So let's move on a little bit, and we'll find classes that are more expressive and have more than 3. So on this slide, yes, I have examples only of 1, 2, and 3, but I'm sure you can imagine classes of functions that are more expressive, and you can easily shatter 3 and 4 points even. But let's first convince ourselves that we agree with these points here. So half intervals, it's 1 because we managed to shatter 1 point, and we argue that no subset, the quantifications here are important, no subset of size 2 can be shattered. For the intervals, we managed to shatter 2, but we argued that no subset of size 3 can be shattered. For the half spaces was a little bit more involved. We managed to shatter set of 3 points, not all sets of 3 points, but we managed to shatter sets of 3 points, right? This was the quantification problem that bothered you. And we argue that no set of 4 points will be shattered. Everyone is okay? So now, and again, this is the issue of quantification that you have to think about. So now that we have this notion of VC dimension, we can quote a theorem, and this theorem is really a simple generalization, not simple. In the way it's written, it's a generalization of what we had before. What are we saying here? We are using VC dimension as the measure of expressiveness of the class of functions, and we can have the same Occam's result as we had before, now for infinite hypothesis space. So what does it say? We're given a sample of M examples. We find some H that is consistent with all M examples. And then I'm telling you that if M is as large as this, then it's going to be good. What does it mean? It means that with high probability, at least 1 minus delta, this H that you found is going to have error less than epsilon in the future. And this condition on M is very similar to the condition that we had before, in the sense that it's inversely proportional to epsilon, makes sense, inversely proportional to delta, also makes sense, and goes up with the VC of H. So the log size of H was replaced here by VC of H. Yes?
Is there a similar bound for the non-consistent?
Yeah, and exactly the same thing is going to work, thanks, for the non-consistent thing, where instead of saying the error is going to be less than epsilon, I'm going to say the gap between the empirical error, the training error, and the error is going to be less than epsilon. Okay, so that's the generalization that we're doing. So essentially, now the error is a shift from 0, which was our empirical error. We were consistent, 0 error. And in general, it's going to be a shift between the empirical error and the true error. Okay, so again, basically, if M is polynomial, either in size of H in the finite case or in VC of H in the general case, we have a Peck learning algorithm. Now, just to evaluate our understanding here, this is a general theorem that is written in terms of VC of H. Now, when we talked about VC of H, we talked about classes of functions that are infinite. But I could also measure the VC dimension of a finite H, right? So let's see if we understand the relation between these. What if H is finite? Are we going to be very different than what's written here, or is it going to be the same? So in order to avoid confusion, rather than talking about M, I'm going to assume that H shatters K examples. So now H is finite, okay? Someone told me it shatters K examples. What can you say about the VC of H? Or what can you say about the size of H? Because I have the VC of H there, and I want to move to the old bound that we had, that instead of VC there, had size of H. So let's think about the size of H here. I told you H shatters K examples. Yes? Yeah.
It has to have at least 2 to the K function.
Excellent. Why?
Because it needs, every labeling corresponds to a different function. So to be able to have all those labelings, you need to have all those.
Right, so let me rephrase what you're saying. So someone promised me, as I said here, that H shatters K examples. So let's look at this K example. What does it mean that it shatters these K examples? it means that for each of the labelings of these k examples, there is a function in H that realizes it. K examples, how many different labelings are there? 2 to the k, right? All subset, take a subset, make it positive, the rest is negative. Every subset of the k is a different labeling, so there are 2 to the k labelings, so I must have in H at least 2 to the k functions, otherwise I won't be able to realize and I won't be able to shatter. So that's basically it. So notice that to shatter k example, it must be that the size of H is 2 to the k. This is just what we said. So the log of this is at least VC of H. So we are consistent here, right? So the fact that I phrase this theorem in a general way doesn't contradict the previous theorem where it was phrased for in terms of size of H. And this also gives us another sort of indirect way to think about the relation between VC and size and understand shattering. Questions? Okay, so now that we have this, let's move back to learning. I mean, this is actually just a tool, yes? This one? Oh, greater than equal to. Good. Yeah, it could be. So, excellent. So it should be, it could be that that's it. They're just exactly 2 to the k functions. Yeah. Okay. So now let's use it. So the real reason we did this is because we want to talk about generalization. This is the last lecture we are really talking about generalization in kind of theoretical way, but we want to be able to use this in order to argue that some classes of functions are learnable. So let's go back to the learning rectangles. So can we pack learn it? Can we show that it's pack learnable? So 2 issues. One is we want to be able to argue about the VC dimension. And once we know about the VC dimension, we'll come up with an algorithm. So what is the VC dimension of the class of rectangles? So again, what do I have to, how do I decide it? So I know what is my instance space. Instance space are points in the plane, right? So I have to consider sets of points in the plane, sets of size 1, size 2, size 3, size 4, 5, 5, 6, whatever, and see what can be shattered and what cannot. So I'm arguing that it's very easy for 1, 2, and 3. Just think about it. And even for 4. So this is a general setting of 4 points. And I want to argue that you can take this set of 4 points and shatter it with rectangles. Right? So if all of them are positive, put a big rectangle outside. If all of them are negative, put the rectangles on this board. If one of them is, for each one of the 4 cases of 1, you can put a little bit rectangle around it and so on. So you can take all these 4 points and convince yourself that it's shatterable. Now notice, again, quantification issue. Not all sets of 4 points are shatterable. Give me an example of one that isn't. All 4 points on one line, I cannot shatter it, but I don't care about it. Right? All I need is a set of size 4 that is shatterable, and I showed you one. Okay, what about 5? So by the way, already now, to answer your question, it's greater or equal than 4, right?
Yeah, I was talking about linearly, like a linear function. So what you're saying is if you create a function that's not linear, then you can shatter.
Yes. It's true that for functions that are linear functions, the VC dimension is 3 in the plane, and in general, in n dimension, the VC dimension is going to be n plus 1. But now we are more expressive than linear functions, right? So we already convince ourselves, given this argument, that the VC is greater or equal to 4. Now let's think about 5. So I wouldn't have stopped on 5 unless I would be able to argue that no set of 5 points is shatterable, right? And let's think about this argument. So, okay, so this still completes the 4. Some set of 4 points are not, but we don't care about it. I do want to care about 5. So the argument for 5 is going to go like this. So I'm going to place 5 points and find the extremes. Take max over x, mean over x, max over y, mean over y. At most, I'm going to have 4 points that satisfy this. It could be that all 5 satisfy this, but I will definitely have 4 points that are on the boundaries of this, right? So, and this allows me to find a labeling that is not realizable. If the 5th point is inside, that's easy. I'm going to put it as negative and put all the others as positive. You cannot realize it. Similarly, if the 5th point is also on the boundaries, I'm going to do the same. I'm going to take this 5th point, make it negative, all the other positive, cannot realize it. So basically what I showed is that no 5 points can be shattered, which means the VC dimension is 4. We're happy, small VC dimension, we can learn. Now, the second component is, can you give me an algorithm? You already know that the sample complexity is small. So it's going to be, if you have an algorithm, VC dimension, it's going to be PEC learnable. What will be an algorithm? You actually gave me an algorithm earlier today. Let's just repeat it. I'm giving you a set of m points. What's your algorithm? Yeah? Sorry? But, right, so basically find the smallest bounding box of the positive examples, and that's going to be consistent with all your data, positive and negative, and you'll find, yes?
So what about the VC dimension makes it calculable? The fact that it's like
it's finite. In fact, yes. So you're exactly right. I didn't have to prove that it's 4. It was enough if I would prove that it's less than 23. Right? From the PEC learnability case, it would have been as sufficient. Right? That's basically your point. It's a good point. I don't have to exactly show what it is. Just for the fun, we show that it's exactly 4. We could have shown that it's, if you had a better argument, show that it's less than 23. It's as good from the perspective of proving PEC learnability. Yeah.
What would be a situation where it would be?
Okay, so that's, so in fact, if you go to complexity theory, given a function class, it's actually the algorithm that computes PEC learnability, the VC dimension. You're asking about VC dimension or PEC?
I'm asking, so it seems like, we found that some hypothesis space has VC dimension 1, some hypothesis space has VC dimension 2. It seems like if we get any constant number, it's going to be PEC learnable. So
Right.
a situation where we get a VC number and say, okay, then it's not PEC learnable.
So let's take the class of all Boolean functions, all decision trees. How many Boolean functions are there? Boolean functions over n variables. We're going finite again, but it's sufficient for this example. So there are 2 to the 2 to the n, right? Because 2 to the n assignments, if I have n variables, and the number of every subset of them is a function, defines a function. I'm taking a subset, say these are the positive, the rest are negative. So there are 2 to the 2 to the n functions. The VC dimension is not polynomial, right? Not going to work. Okay? So the class of all Boolean function is not learnable. And you can think about, I gave a list in one of the slides last time of a few other examples like this. But basically, it's just way too expressive. The class of function is way too expressive. It's not back learnable. But in this case, whenever you tell me, it's finite, it's less than 7 or something like this, it's good enough. By the way, you gave us an algorithm. In real life, will that be the algorithm that you use? Or would you change your hypothesis a little bit? So the algorithm that you gave me is find the smallest bounding box, that is the smallest rectangle that contains the positive examples, which means it's not going to contain any negative example because I promised you that the data is consistent with an axis parallel rectangle. In real life, which one would you choose? Would you choose this as your function? Or would you do something else? Yes?
No, because this is too restricted. Because it's possible that you could get another positive example that's outside of it. So it'd probably be a better way, and a better way of doing it would be like take the average between the smallest possible bounding rectangle for the positive and the largest possible bounding rectangle for the negative.
Yeah, excellent. So basically what you want is you want to have some margin, right? So you look at this. This is the smallest one that contains all the positive. You want to enlarge it on all 4 sides until it hits the negatives, and then maybe go middle way, right? This way, you feel intuitively that it's the safest place to be to prepare for new examples. Midway, because I don't have any other reason to do, third way or 3/4 ways. If actually you see that there's a lot of density on the right side of the rectangle, and it's very sparse on the left side, maybe you will go 3/4 of the way on the left side and 1/4 of the way on the right. So you can play with it a little bit. But the basic idea, given that we have no other information, I just want to enlarge it and be somewhere in the middle, because I feel that I'm safer this way and more prepared for new examples. This is exactly the idea of thick separators, right? When we talked about linear separators, we're going to talk about this in 2 weeks again when we talk about SVM, 2 weeks. Okay, so we proved that we can learn something, anything in class of functions. One more comment before I'm summarizing. We always talked about upper bounds. That is, if M is at least this many examples, everything is going to be fine, right? So if you train on M examples, where M is at least as large as this, the future is going to be good. In fact, people can also prove lower bounds. That is, these lower bounds would say, if you don't see at least these many examples for your training, things are not going to be good. Right? So it's not only upper bound, there are also lower bounds. Now, lower bounds are, as usual, they are very strict. They say, what does it mean that things are not going to be good? Maybe in most cases things are going to be good, but lower bound means that there is some distribution and there is some class of functions such that if you haven't seen these many examples, it's not going to be good. So, and you can see that the bound is conceptually similar to what we had before. It's it goes with VC dimension, it goes with 1 over epsilon, it goes with 1 over delta, as before. So the bounds are actually relatively tight. Okay, so let me summarize what we've done. So we talked about the PEC framework. The goal was to provide a model so that we can theoretically think about the effectiveness of learning algorithms. Will they work in the future? We don't want just to do learning for a given data set and say, oh, for this data set it works, we're happy. We want to be able to have a general theorem that is not specific to a learning algorithm, is not specific to a data set, and that allows us to quantify how well are we going to do in the future. So what we found is that the sample complexity, which is the key parameter, for every consistent learner using the hypothesis with H can be determined if we measure H's expressiveness, either size of H or VC dimension of H. And we then generalize this also to the non-consistent learner, what I call the agnostic learner. And again, we quantified the sample complexity needed to guarantee generalization in terms of size of H and VC of H. So why do we care about sample complexity? Really, they are not tight. It's well known that they are not tight, but they give us two advantages. One is they allow us to separate what can be learned from what cannot be learned, with the example that we've given before. And even more importantly, they guide us to try and use smaller hypothesis spaces. And we will see, again, when SVM is the best example for this, the VC dimension notion, even though algorithmically you don't touch it, guides the selection of the model, the specific hypothesis that we choose. We are choosing it so that it's going to minimize VC dimension. Now, you don't need to do it. You can just plug in a function from scikit-learn and use it, but we are going to show that the way SVM works, really, it chooses the function that is minimizing the VC dimension within all the possible hypothesis spaces. So really, this is going to be guided by theory. We also talked a little bit about computational complexity, but the key thing is that this theoretical framework allows us to really think about complexity of learning and feasibility of learning. So there's a lot more done in this area, which I'm not going to talk about. So there are models that extend the PEC learning model to models that deal with noisy data, with specific distributions, relax the distribution free assumption. There's some distance between the training distribution and test distribution. You can learn neural network, you can learn probabilistic representation, you can do a lot of other things. All of them extend this framework in various ways. One important extension is this extension that relaxes the distribution free and instead makes some assumptions on the prior distributions over the hypothesis. So some hypotheses are more likely to be chosen than others, and if you place a prior distribution over it, you get something that is called the PEC Bayesian theory. So I haven't talked about any of these. People that are interested can use these as search queries and keep on going. What we are going to do is we're going to use these as insight into specific algorithms. Specifically, as I already said, SVMs were directly guided by PEC learning theorem. Boosting, that we're going to do in about a week and a half, is a very important algorithm that was directly guided or invented as a solution to a PEC learning problem. I'm going to talk about it when we get there. So the value of this model goes beyond just understanding learnability. It really gives practical algorithms or gave rise to practical algorithms. Okay, let me stop here. Remind you that there's recitations this afternoon and some office hours today, tomorrow, and the exam is on Wednesday.
question, but I wanted to ask about the term packed learnability versus agnostic learning. I mean, are these two mutually exclusive? They don't seem to be, right? Like, is agnostic learning just a way of saying that the algorithm was not consistent with the examples,
Yes.
but it can still be packed learnable?
Oh yeah, it will be packed learnable.
That the packed learnability is still just a function of the size of the hypothesis space and the computational complexity of actually running an algorithm that does it.
So the slide that I have with the title agnostic learning is a packed learnability result, right? So yeah, so these are
agnostic
independent
learning just
things.
means when you're not consistent.
Exactly.
Okay.
You talked about saying that the class of Boolean functions is not patternable. I don't really get why.
Because the results that we had says that m has to be polynomial in the complexity parameters, and in this case it's exponential.
If we train n data points using a classifier and we get the training accuracy about 97%, so can we say the BC dimension h is greater than n?
No, BC dimension has nothing to do with the error that you make on the training. I mean, BC dimension is a notion that has to do with the hypothesis space. It has nothing to do with the training data. I don't know that you're going to see training data, right?
Yeah, I understand what you say, but I just see the question in the previous meetup and I just confused about it. Is that
So I don't remember what was the question there,
yeah?
but
question.
why didn't you ask it in class? This is the question you should have asked in class. Half the people are interested. So take this little recitation out and ask it there, because I think many people will care about this. Yes, so I don't remember the question, but as I said, someone asked the question. VC dimension, just you take points from the instance space. It has nothing to do with the learning. Maybe I will not learn it. Okay? Yeah.
I'm a little confused about why 5 instance is not shutterable, because I understand why if you make this middle point negative, it's not. But if you make it positive, doesn't that make it shutterable?
Yeah, but again, what is shutterable? You have 5 points. 5 points have how many different labelings on them? 2 to the 5, 32. To be shutterable means that for each one of the labelings, there should be a function. There should be a rectangle that separates them. Here is a labeling. Put this negative, the rest positive. No labeling, no rectangle can realize it.
Ah, I see.
Okay?
Oh, so like, okay, so then for VC space, as long as like one set is shutterable, it's okay, but then for this case, like for 5 points, since
No.
none
What you said at the beginning is right. At least one point has to be shutterable. One set has to be shutterable.
Yeah.
What does it mean to be shutterable?
like all labeling.
All labels, right? So 4 points were shutterable because I found a set of 4 points that all 16 labelings were realized using a rectangle. For 5,
Not all coloring works.
no set of 5 points, you can do all 32.
Yeah.
So that's it.
Okay, yeah.
Okay, so it's subtle, You have to
Yeah.
think about it, yeah. Sure. Oh.
So just now in class, you mentioned that it is track learnable if it's polynomial in the BC dimension, but in the exam, they said that if the hypothesis class has a finite BC dimension, then it's not polynomial. So is that wrong, or does it have to be explained?
If it's finite, it's polynomial.
If it's 2 to the k, it's still everyone can also 2 to the 2 to the k.
I mean, it's large, but it's still finite, even if it's exponential.
If k is fixed, 2 to the k is still fine. Right?
So in I guess in the lecture
Right. And what's wrong here?
Finite.
Okay, so any hypothesis that with finite visibility is calculable. This does not say that if it's so what do we want to, what bothers you here? So if it's finite, okay, if it's finite then it's exponential in what?
For the example you gave in class, it would have been n variables, then it would be 2 to the n possible because of 1 to the x plus 2.
No, but then we didn't. Then we talked about the size of the mesh. Okay, let's see if we can clarify this further.
Has to be finite. But are we getting dimensions? Are we
So if the hypothesis size is finite, then there's no problem, right? So the log of the hypothesis size has to be polynomial in the complexity parameters. Now let's talk about the infinite case. But this is, by the way, finite case, right? I don't remember this formula. Yeah, DTK was a finite hypothesis case, right? Maybe it was infinite. Maybe it wasn't.
An extension for like a percent point reduction because I have like really a lot of stuff that I receive and I'm not eating.
Yeah. What sort of extension were you considering?
Sorry?
What sort of extension were you considering?
Just like just 1 day.
You're just gonna take the day.
Like, but like I like with the leap day and then another
with
day.
the leap.
Yeah.
I see. 10%? No. Just keep it the extension.
Are you-
Without it as a point deduction.
No, I can take 10%. It's okay. Are you sure? Okay.
Yeah.
Thank you so much. I'm like struggling right now.
Yeah,
Thank you.
Everybody is.